Hello and welcome to this video on determining if a transformation is one-to-one, or another word for a transformation being one-to-one is a transformation being injective. But for the most part I'll use the words one-to-one in this video. So I'll start off by defining what it means for a transformation between two vector spaces to be one-to-one. I'll define it in a couple ways actually, and one of those ways will be very important for us in order to to prove that a transformation is indeed one-to-one. Okay. So, what does it mean for a transformation to be one-to-one or injective? You may see this word in some textbooks. All right, a transformation T, from V into W, say V and W are arbitrary vector spaces, is one-to-one when the pre-image of every element in the range of T consists of a single element of the domain. So remember, the range of T is not always W, right? W is called the codomain, right? V is the domain, W is the codomain. The range of a transformation is the set of all outputs, right? The range is actually a subset of W, not exactly W all the time. So don't confuse the range of T and the codomain. So if you look at every output, every value, every element that's in the range, its pre-image consists of a single element in the domain, meaning that every value in the range or every element in the range is mapped to by T by a single element in the domain. Right. Now an equivalent way to say this, right, and this is going to be very important, I put it in a little bubble here, a little cloud, because this is what we're going to use, this concept, to help us prove or show that a transformation is one-to-one. So equivalently, T is one-to-one if and only if for all vectors in V, if you take two vectors in V, U and V, in the domain, then if T of U equals T of V, meaning the image of U under T is equal to the image of V under T, where the outputs are the same at U and V, then U must be the same as V. Okay, they can't be different, because if T is one-to-one, that means that two different inputs cannot go to the same output. All right, so if we're starting with the output being the same, if T is one-to-one, then these inputs, the U and the V, can't be different. Right, they have to be the same as well. Because if you find, right, and this is a way that you show a transformation is not one-to-one, if you find two different inputs, two different elements of the domain that map to the same element of the range, the same output, then it's not one-to-one. Right? That cannot happen in a one-to-one transformation. All right, so I'm going to keep this in mind here. I'll bring this back in the examples coming up. All right, so here's some pictures, just some simple pictures demonstrating the concept of one-to-oneness or injectiveness of a transformation. All right, so here I have a picture of a mapping, right, a little arrow diagram with a very simple transformation, simple function. So here's a transformation called T here. And my domain consists of just three elements, say A, B, and C, three vectors. And the codomain, right, consists of four elements or four vectors, four numbers, whatever. And I have a little arrow showing you the mapping. A is assigned to the number 3. A maps to 3, B maps to 4, C maps to 1. Okay, so this picture is a picture of a one-to-one transformation, or an injective transformation. So T is one-to-one, right? And the reason being is look at all the values of the range, right? The range of T is all the actual outputs, all the actual images of the domain elements under T, right? 1 is mapped to, 3 is mapped to, 4 is mapped to, so the range of T is just the elements 1, 3, and the set of elements 1, 3, 4, right? Notice that 2 is not in here, and as I mentioned at the very first page, right, the range of a transformation isn't always going to be the codomain, right? This is not the range, 2 is not in the range here. And then notice that every single one of these is mapped to by only one element of the domain. 1 is mapped to by only the element C, and that's it. 3 is mapped to by only the element A. 4 is mapped to by only the element B. Right, so and those are the pre-images, right? The pre-image of an output is just the set of all the elements that map to that output. So if you look at every element of the range here, right, the pre-image of 1, as I mentioned, was C, right? So it's the set with C in it. The pre-image of 3 is A, right? 3 got mapped to by A. The pre-image of 4 from the range is the element B from the domain, the set with the element B, because 4 got mapped to by B. And you see here, every element of the range has a pre-image containing only one element, with C, with A, with B. And if that has to happen, that has to be the case when the transformation is considered 1 to 1. All right. All right, then on my next page, I've got a simple example. Again, just a simple little mapping with finite numbers of elements in the domain and codomain. So here's another picture similar to that. Again, I'll call it transformation T. My domain elements are A, B, C, D. My codomain elements are 1, 2, 3. You see A maps to 2, B maps to 3, C maps to 1, D maps to 2. All right, and do you see the issue here? Right? Why T is not 1 to 1? It's because of that element 2 that's in the range, right? This is a problem. See how 2 is mapped to by more than one element, right? By A and D. So this is not by definition 1 to 1, right? Again, so I wrote the same stuff, the range of T this time is, it looks like every element in the codomain is mapped to 1, 2, 3. So here, the range is the codomain. That can happen. And then we look at the pre-image of each element in the range, right? The pre-image of 1 was, the set with just C in it. So far so good. The pre-image of 2 is, right? Again, I mentioned this already. It has A and D in it. And the pre-image of 3 has just B in it, but that doesn't matter, right? As soon as you find one element of the range that has more than one element in its pre-image, right? Has more than one element that maps to it, your transformation is not 1 to 1, is not injective. So there is an element of the range that has more than one element in its pre-image, not 1 to 1. Okay. All right. So just a quick little, some quick little pictures to demonstrate the concept. So now we're going to get into some actual descriptions of transformations, some actual rules, and we're going to be asked, to determine whether the transformation is 1 to 1. Right? Does it satisfy that definition? So this is where my statement in the cloud on the first page here, this little blue cloud, is going to come into play. We're going to assume this. All right, so first of all, we're going to take a couple vectors. Imagine we have a couple vectors from the domain. Then we're going to assume that their images are equal. And then we would like to show if possible, right? If possible. If it's not possible, then it's not, then that probably means the transformation is not one-to-one. But we're going to assume that the images are equal. Their outputs are the same. And if it is one-to-one, and you have two equal outputs, then the inputs must be the same, because again, if the outputs were the same but the inputs were different, then you would have something that's not one-to-one, right? You have two different inputs going to an equal output, to the same output. All right, so we're going to use this a lot right here to show one-to-oneness or injectiveness. So my transformation here is T, and it's from R2 to R2. Assume the standard operations for these vector spaces that have been brought up in previous videos. If you've been watching, just standard vector addition, standard scalar multiplication here. And the rule is T takes a vector from R2 with components x1 and x2, and the output, T of this is equal to 5, another vector from R2 with 5 times x1 for the first component, 5 times x2 for the second. All right. So to show that this, trying to show that this is one-to-one. So let's take a couple vectors, say u equal from the domain, right? From the domain, u equals, and again, just some generic vectors. General vectors use variables, not specific numbers here. Say the components of u are, u1 and u2, just so I know it's from u. And another vector v with, say, components v1 and v2. And these belong to the domain, right? The R2. And again, this is the domain R2, not the codomain R2. And we're going to assume that their images are equal. We're going to assume that the image of u under T, so T of u, we're going to assume that this is equal to the image of v under T. All right. Now, if we can show, right, if we can show that u is equal to v, right, if we can show now that vector u is equal to vector v, well, then that means that if two vectors have the same image, they're the same vector. They're not two different vectors, two different inputs with the same output. Therefore, T must be one-to-one. If we can show u equals v here, then T is one-to-one. All right. If we can't show this, then we can probably think of a counter example. We can think of we can probably come up with, and I will, if it ever comes up, if we ever need to, and I will in this video. But if we can't show this, let me finish this sentence here, right? And T is one-to-one. But if we can't show this, then there's probably a counter example you can show, meaning you can find two different vectors u and v that have the same output. And again, that's not going to happen in a one-to-one transformation. All right, so what does this look like? Well, T of u would be 5u1, 5u2, and T of v, if I plug v into T here, would be 5v1, 5v2. All right, and then in order for two vectors with these components to be the same, this means the components have to be equal. This would tell me that 5u1, again, if I'm assuming this, that means that 5u1 must be equal to 5v1, and all I would need to do is simply divide both sides by 5 to show that u1 is equal to v1. All right, so right now I've shown that the first component of u is equal to the first component of v. So I'm like halfway there. Now I just need to show that the second components are equal, and then we'll have the statement u equals v, and therefore, since when the outputs are the same, the inputs are the same, t would be 1 to 1. So we have in order, again, these are equal, so the first components are equal. The second components are also equal. We'd also have 5u2 would be equal to 5v2. And again, simply dividing both sides by 5 here, it's very clear to see that u2 must be equal to v2. So now I've shown that if we assume this, then u2 must be equal to v2. The second components of u and v must be the same. All right, so putting these together, we are seeing indeed vector u must be equal to vector v, right? So if two outputs are equal, right, if two outputs are equal, their inputs must be the same input, right? So not two different inputs going to the same output. Therefore, t is a one-to-one transformation. T is 1 to 1. Great, and that's really all we're doing. All right. Again, now that one was simple. And it's not always that simple, but it can be, as you've seen. But this is what I'm trying to do. Right? I'm going to assume this. I'm going to assume, again, start with a couple generic vectors from the domain, assume their images are equal, and then try to show that the inputs would also be equal. And then you'd have a one-to-one transformation. Again, if you can't show this, then you might want to try to find a counter example, right? Find two different vectors from the domain that have the same output, and therefore t wouldn't be 1 to 1. All right, so my next example is another transform. Now, the first few examples I have here are transformations between Euclidean spaces. You know, the last one was from R2 to R2. This is from R2 to R3. All right, we'll get to some examples in a minute. Well, more than a minute, but in a few. Between just other vector spaces, so bear with me here. So again, I'm trying to see, is T 1 to 1? Is it injective? So again, I start off with a couple vectors, just some generic vectors from the domain from R2, and what do those look like? Any vector from R2 looks like this with two components. So I'm going to do the same thing I did with the last example. Say u is equal to the vector with components u1, u2, and another vector from the domain v is another vector with two components v1 and v2, and these belong to the domain. All right, and we're going to assume that their images are the same. All right, under this transformation. So the image of u under t, we're going to assume that that's equal to the image of v under t, and then try to show that u is equal to v. If I can show that the inputs are the same, then we have a one-to-one transformation. All right, so show that u1 equals v1 and u2 equals v2, basically. All right, so what does t of u look like? So I apply, replace x1 and x2 over here with u1 and u2. So this would be 5u1 minus 3u2, and then the second component u1 plus u2, and then the third component u1 minus u2. All right, and this we're assuming this is equal to the image of v under t. So I apply the t to v here, just replace x1 and x2 with v1 and v2, so 5v1 minus 3v2, then v1 plus v2, and then v1 minus v2. All right, and then from this we get the following system. You can think of it as a system of equations here involving these u1, u2, v1, and v2. In order for these to be equal, like we're assuming, 5u1 minus 3u2, right, must be equal to 5v1 minus 3v2. Then u1 plus u2 must be equal to v1 plus v2. And u1 minus u2 must be equal to u1 v1 minus v2. All right, and then we're trying to see if we can manipulate this a bit. Now you could set up a weird, like, put all the things, variables on one side and zeros on the other, and then you have your columns. You could create an augmented matrix where each column has the coefficients of each variable, and create a little 3 by 5 augmented matrix here. But I'm just seeing this right away here. If you were to add these equations together, the equation 2 and equation 3 here, left side you see the u2 and negative u2 would go away when you add them. You'd have 2u1 would be equal, and then the same thing on the other side, the v2s would go away. You'd have 2v1, and dividing both sides by 2, you'd be able to show that u1 must be equal to v1. Alright, so I'm done with half of this, right? I've shown that, the first components of u and v must be the same. And if now that u1 is equal to v1 here, right? Anywhere I see a u1, I can replace it with v1. So just so I don't clutter down here too much, this would be 5. I can replace u1 with v1. So this is 5v1 minus 3u2 equals 5v1 minus 3v2. And then now I can subtract the 5v1 from both sides, and then divide both sides by negative 3. Do you see how u2 would have to be equal to v2 also? So in this system, right, here, yes, u1 would have to be equal to v1, and u2 would have to be equal to v2 in order for all these to be true. All right. So what we're seeing is from both of these, yes, therefore u must be equal to v, right? So if two outputs are equal, their inputs must be the same and not different, right? Therefore there aren't two different inputs that give me the same output. Therefore this is a 1-to-1 transformation. Right. So t is 1-to-1 again, right? So my first couple examples were transformations that were 1-to-1, right? I know it wouldn't be a good video if I didn't come across some examples of transformations that weren't, and let's see what the next one looks like. So here's another one between two Euclidean vector spaces, R2 to R2 again. Alright, and then again, here's the transformation. So it takes xy to x minus y, y minus x. Sorry, two-component vector to a two-component vector. Alright, so I'm trying to see if t is 1-to-1. Alright, so I'm going to just take some generic vectors from R2 from the domain. And I'll call this u1, u2, and another vector v from the domain. And just some general vector v1, v2. These belong to the domain, and we are assuming that their images, the outputs, are equal at these inputs. Right, the images are equal. So we're assuming that the image of u under t is equal to the image of v under t, and then what we're going to try to show, if we can, is that u is equal to v. If we can show that u is equal to v, right, so u1 equals v1, u2 equals v2, then this will be a 1-to-1. If we can't show it, if it seems like, oh, they might not be equal, then I'm going to try to think of a counter example, and you might be able to think of one already, but two different inputs that give me the same output. Right. So let's go through here. Now, what would t of u be? All right, again, I'm just replacing x and y over here in the rule with u1 and u2. So it'll be u1 minus u2 for the first component, and then u2 minus u1 for the second component. All right, equals, and then replacing, the x and y with, v1, v2, the image of v under t would be v1 minus v2, v2 minus v1. Right, again, I'd be getting the following system. The only way these two are going to be equal is if u1 minus u2 is equal to v1 minus v2, and if u2 minus u1 is equal to v2 minus v1. Well, look, aren't these really just the same equation multiplied by -1? And if I just go times -1 on both sides here, I would get this equation, wouldn't I? So really one of these is unnecessary, right? One of these depends on the other, so I don't need this second one, right? And you've seen that before with dependent column vectors, dependent row vectors. If one equation or one row or one column can be written as a linear combination or a scalar multiple of other rows or other columns or other equations, that particular row column equation isn't necessary. All right, and then I'm solving this. Now, does this imply that u1 and v1 have to be the same, and u2 and v2 have to be the same? No, it doesn't. No, it doesn't. Right? This does not imply that u1 has to be equal to v1 and u2 has to be equal to v2. Right? Because, think about it. As long as u1 minus v1, right, if I rewrite the equation a little bit, say I subtract v1, I got u1 minus v1 on one side, and then add u2, you got u2 minus v2. So as long as u1 minus v1 is the same as u2 minus v2, or as long as u1 minus u2 is the same as v1 minus v2, this will be true. T of u will be equal to T of v. Well, think about it. I could have u1 be 3 and u2 be 5, right? 3 minus 5 is -2. And then I could have say v1 be 7 and v2 be 9, and this would be a true statement, wouldn't it? 3 minus 5 is the same as 7 minus 9. They're both -2. But the vectors u and v wouldn't be the same. All right, and there's my counterexample. All right, there's my counterexample to the one-to-oneness. I'll put that over here. Counterexample. So suppose u was 3, 5. 3, 5. And v was equal to 7, 9. Now, do you see how their images would be the same? Right? T of u would be the same as T of v. Right? If I plugged either one of these into this, you'd have, the first component would be 3 minus 5, so -2. Or 7 minus 9, -2. And the second component would be the other way around. 5 minus 3, 9 minus 7 would be +2. For both of them. So T of u is equal to T of v, but u is not equal to v. Right. Right, and if you thought about it like with my little mapping, right, with the little dots and arrows before, you could think of it like this. Here's little dots representing the vector, 3, 5, and the vector 7, 9 from the domain. And then over here in the codomain, I have the vector -2, 2, right, as an output. And both of these map to -2, 2. So it's not 1-to-1, right? Another way to say this, I have found an element in the codomain. I've found an element in the range, right? This is an actual output. I have found an element of the range that has more than one element that maps to it, right? I have found an element in the range that has more than one element in its pre-image. All right, so that's why. So this counter example here with these specific vectors show me that from both of these here, T is not one-to-one. Okay, T is not one-to-one. It's very clear just from this one example, and that's all you need to show. That's all you need to do to show that a transformation is not one-to-one. If you can find just one example, one specific example of two different vectors that have the same output, then it's not one-to-one. Right? So again, you start with this, right? Again, you take two vectors from the domain, assume their images are equal. You try to show that the inputs are the same, that the vectors you have are the same. But if you can't, like I couldn't here, I couldn't show that u1 was equal to v1 and u2 was equal to v2. I couldn't. Then there's probably there's a good chance you should be able to find a counter example, show that is not one-to-one. All right. Next example. Now I'm getting into some examples where not every single vector space is one of the Euclidean vector spaces. So here's a transformation from P2 to R2, right? Remember this P2, P3, P whatever subscript. This is the set of all polynomials of degree 2 or less. And then this is your typical Euclidean R2 here. So here's the rule, right? T takes a polynomial of degree 2 or less, which always look like this, ax squared plus bx plus c, or whatever order, c plus bx plus a squared, whatever order you write those terms in, where a, b, and c are the coefficients of the variable x, right? A, b, and c are numbers. And the output is a vector from R2 where the first component is a squared, the second component is b. Right? All right, so again, we're trying to show if we're trying to determine if t is one-to-one or not. So I'm going to take two vectors. So I'm going to let u equal just one generic vector from P2. I'll just use ax squared plus bx plus c. All right, what every vector in P2 looks like, some degree 2 or less polynomial. And v also belong to P2. Dx squared, just something with different letters. All right, dx squared plus, and I don't usually like to use e, so fx plus g. All right, these belong to the domain P2. And we're going to assume that their images under T are equal. So we're going to assume here that T of u is equal to T of v. And we're trying to show that these two polynomials are the same, right, if this is the case. All right, because if this is the case and you show that u is equal to v, then T is one-to-one. If you can't show that u is equal to v, then you should come up with a counter example, to find two different polynomials that have the same output, and therefore T is not one-to-one. Okay, so what is T of u? All right, and also, in order to show that two polynomials are the same, you just have to show that the coefficients of like terms are the same. So I need to show that a equals d, b equals f, and c equals g in order to show that u equals v. All right, so what does this mean? What's T of u? If u is this ax squared plus bx plus c, well, it looks the same as that, so the vector a squared b comes out, right? That's the image of u under T. And what's the image of v under T? I'm just replacing a, b, c with d, f, and g, so it'd be d squared f. And in order for this to be true, we'd have a squared would have to be equal to d squared, and b would have to be equal to f. Now this one's good. This is good here. If b is equal to f, that's part of it, right? I'm trying to show that b equals f, c equals g, and a equals d. If a squared is equal to d squared, does that mean that a and d have to be the same number? No, right? Not necessarily. This does not imply. Now, if those were odd powers, a cubed equals d cubed, and we're talking about real numbers here, then a and d would have to be the same. But even powers are different. All right, this does not imply that a has to be equal to d. For example, isn't 2 squared the same as negative 2 squared, right? Both of these are equal to 4, but 2 is not equal to negative 2, right? So just because two numbers have the same square doesn't mean the bases have to be the same. So just because a squared and d squared are the same does not mean that a equals d. So it may not be the case that u is equal to v. Basically we're saying here that u is not always going to be equal to v when t of u is equal to t of v. So I feel that this particular transformation is not one-to-one. Also, notice how c and g aren't even mentioned here, and we're trying to also show that c and g are equal. Basically it looks like c could be anything and g could be anything else. So also we're not even showing that c equals g. So I'm thinking very much so that this particular transformation is not one-to-one. And I will just simply think of a counter example here. Counter example where a squared equals d squared. Like I said, I'll just have one where a is 2 and one where where d is negative 2. Let's just do this. Let's have u be 2x squared. Right? There's a polynomial degree 2 or less. And I'll have v be negative 2 times x squared. So here, the lead coefficient's 2, and then the other coefficients are 0, right? And here the lead coefficient is negative 2, and the other coefficients are 0. So the images are the same, right? Both t of u and t of v are the same thing. Both would yield the vector 4, 0, wouldn't it? Right? Because you'd have 2 squared, 0, and then negative 2 squared, or 4, 0. You'd have 4, 0 as both the outputs for these. But u is not equal to v. These are not the same polynomial. And just like I did earlier, right, if you were drawing a little mapping picture, right, again, imagine these little dots here represent elements of the domain. I have, 2x squared is in the domain, negative 2x squared is in the domain, and then the vector 4, 0 is in the range, right, in the codomain, but also in the range. And then we have this maps to that, and this maps to that. So we have, again, we have found an element of the range that has a preimage that has more than one element. Right? We have an element of the range that is mapped to by more than one element of the domain. So t is not one-to-one. Or not injective. Right? Okay, wonderful. All right, so I've got just a couple more examples here before I talk about, I wanted to go through a few in which, not every vector space was Euclidean. All right, so again here, t is from P2 again, so this is polynomials of degree 2 or less again, and the output's just going to be a real number, just a number. And the value of t, the image of p of x, this is, and this p of x is a polynomial of degree 2 or less. The image of this under t is going to be the integral from 0 to 1 of that polynomial. All right. So as before, let's say u, vector u is, now again, I'm just going to take some polynomial here. Right? That looks like, let's say again, ax squared plus bx plus c, some polynomial from p2 like I had before. And again, I'll have v be, dx squared plus fx plus g. All right, both of these belong to the domain, right? Polynomials of degree 2 or less. And we're going to assume that their images are the same under t, right? That t of u is equal to t of v, and then we're trying to show, if we can, right? If we can, we're trying to show that u is equal to v. And hopefully that's the case, and then t would be 1 to 1. So basically, again, we're trying to show that a equals d, b equals f, and c equals g. All right, well, t of u, that'd be the integral from 0 to 1 of ax squared plus bx plus c dx, and t of v would be the integral from 0 to 1 of dx squared plus fx plus g dx, right? Remember your calculus, right? This can be a number. Now if I do the antiderivatives, it'd be a divided by 3 times x cubed plus b divided by 2 times x squared plus cx, and I plug in 1, plug in 0. So this is going to be a divided by, and then subtract them, and then I have so I have a divided by 3 plus b divided by 2 plus c on this side, and on this side I'd have pretty much the same thing except for d, f, and g instead of a, b, and c. D divided by 3 plus f divided by 2 plus g. Right. So these would have to be equal, right? If I'm assuming that the images of these under t are equal, then these would have to be equal. Now, does this imply that a has to be equal to d, and b has to be equal to f, and c has to be equal to g? No, it doesn't. Now, I could have a and b be 0, and c be, 5. Let me do that here. I could have a be 0, b be 0, and c be 5. And then have d be 0, f be, f be 4, and g be 3. And it would be the same thing, wouldn't it? Because it'd be 0 plus 0 plus 5. You'd have 5 on the left side, and then 0 plus 2 plus 3, 5 on the right side. So this equation here, this does not imply, does not imply that u equals v. All right, not. And I just showed you an example of where some values of a, b, and c, and some values of d, f, and g that would make this true. But a, sure, a is equal to d in my choice, but b is not equal to f, and c is not equal to g. So these polynomials would. So there's my counter example. Right? These polynomials wouldn't be equal. So it looks like this is not 1 to 1 again. So there's my counter example. I'm going to let u be, and I'll just use these values. So I'm just going to let u equal 5, right? Where a is 0, b is 0, and c is 5. That's a polynomial of degree 2 or less. And I'm going to have v be, d is 0, f is 4. 4x plus 3. There's a polynomial of degree 2 or less. And what we're seeing here is that their images under t would be the same. Both t of u and t of v would be equal to 5. And you can check it out. Integrate 5 from 0 to 1, you get 5. And then integrate 4x plus 3 from 0 to 1, you would also get 5. All right. So t of u equals t of v, but clearly these are not the same polynomial. U is not equal to v. And again, so you have two different inputs that go to the same output, right? These two elements of the domain go to this element 5 of the range, right? So I have found an element of the range that has a pre-image with more than one element in it. So yet again, T is not 1-to-1. Okay. All right, so I got one more example here before I get into a very important relationship between one-to-oneness and the standard matrix of a linear transformation. All right, so here, got a transformation between vector spaces P2 and P4. So these are polynomials of degree 2 or less. These are polynomials of degree 4 or less. And all the transformation is doing is taking the polynomial of degree 2 or less and multiplying it by x squared. Right? So it takes p of x and multiplies it by x squared, and get you can see it up here, see it down here. Right? All right. So again, we're trying to see is this 1-to-1. So as with the last examples, I'm going to let u be ax squared again something from P2, some generic vector from P2. And v also be some generic vector dx squared plus fx plus g. All right, these are from the domain P2. And we're going to assume that their images are equal. All right, we're going to assume that the image of u under t is equal to the image of v under t. All right, and we're going to try to show that u and v must be the same polynomial. Now again, to show this, you'd have to show that a equals d, b equals f, and c equals g. Right? As again, the only way polynomials are equal is if they're, the coefficients of like terms are the same. All right, so what's t of u? That would just be ax, again, multiplying these by x squared, right? So ax to the fourth plus bx cubed plus cx squared, right? This must be, we're assuming that this is equal to t of v. So dx to the fourth plus fx cubed plus gx squared. And look, we have it, right? You have a polynomial equal to a polynomial here. This does imply, that a must be equal to d, right? If these are equal, the coefficients of the x to the fourths must be equal. The x cubed coefficients must be equal. B must be equal to f. And the coefficients of x squared must be equal. C equals g. And putting these together, that tells me that vector u there, that polynomial for u, must be equal to the polynomial for v. All right, so this is telling me that there aren't two different inputs that give me the same output. This is a 1-to-1 function. T is 1-to-1. Great. All right. So now, I would like to talk about the relationship between one-to-oneness, right, or injectiveness, and the standard matrix for a linear transformation, right? So far, I've been looking at transformations, without talking about whether or not they're linear, right? Remember, a transformation is linear if it satisfies that additivity property and homogeneity property that have been discussed in prior videos, so I'm not going to go over that stuff again. And also, if you had a linear transformation, then you had a corresponding what was called the standard matrix for that transformation. You could write or express or represent your linear transformation as a matrix transformation as well, where you have a matrix times the input vector as your output. All right. So suppose T from, again, vector space V to vector space W is a linear transformation. All right. T is 1-to-1 if and only if the columns of the standard matrix of T are linearly independent. All right. So what we're going to do in this next several examples is I'm going to go over examples of transformations we've already seen. All right. Now, not all of them were linear transformations. Let me show you this one here. All right, so you're not going to see this one again. from P2 to R2, where ax squared plus bx plus c map to a squared b here. This transformation was, and you can go and show it on your own if you'd like, but this transformation is non-linear. Okay, so I'm not going to apply what I just said here to this example. All right. But all the rest of them, right, I'm going to do all the rest of them again, but involving the standard matrix associated with that transformation. All right, and what we're going to do to, again, it was very simple to show that the columns of a matrix were linearly independent, right? You just put that matrix into an echelon form, whether it be reduced echelon form or just echelon form. And if every column is a pivot column, then all the columns were linearly independent. And if, not every column is a pivot column, then the columns of the matrix are not independent, they're dependent. All right. So the first example was this one, right? This is a linear transformation, and I've rewritten it again. And what we saw earlier, all right, so I'm gonna bring up another page with this example, but it's gonna be blank, all right, just with this written. We saw earlier that it is one-to-one. All right, so what we're going to see is that when we take this linear transformation and find the standard matrix representation for it, and put that standard matrix in, an echelon form, every column will be a pivot column, right? All the column vectors will be linearly independent. And really, I don't need to do echelon form for this. Yeah, I guess maybe I should. All right, so here it is. All right, so we saw that it was one-to-one. All right, we saw that it was one-to-one earlier. Now, remember these transformations between Euclidean spaces. If they were linear, right? This is a linear transformation. It was very easy to write it as a matrix product. I'm going to have a 2x2 matrix here, right? Instead of 5x1, 5x2, this output. I can set up a matrix where down one column, down the first column, I have the coefficients of x1, so 5 in the first component and 0 in the second. And then down the second column, the coefficients of x2, 0 and then 5, times the input vector x1, x2. Right, and there's the standard matrix, right? This 2x2 matrix right here. And again, I put up videos before on finding the standard matrices of a linear transformation or a matrix transformation. So again, I'm not going to go into the whole process again. I'm just going to write them, and we'll see that they do have linearly independent columns or not, and that'll tell us whether or not the transformation T is one-to-one. So here's the standard matrix for this transformation, for T, this 5, 0, 0, 5. Now, it's already in echelon form, row echelon form, right? If you look down each row, the first non-zero entry has zeros below it, right? First non-zero entry, 5, has zeros below it. First non-zero entry, 5, there's nothing below it. So this is already in echelon form. Right, and I'll say this, it's in echelon form. Not reduced, right? To put it in reduced echelon form, I just make sure that all those leading non-zero entries, all those pivots are 1. So I'd multiply this by a fifth and this by a fifth, and then make sure that there are zeros below and above, right? Not just below the pivots. So hopefully you can see that if I were to put this in reduced echelon form, it would be the identity matrix, right? 1, 0, 0, 1. But this is already in an echelon form. So look at the pivots, right? Those leading non-zero entries in each row. This 5 here with the zeros below it, right? And then this 5 here. You see how each column, right? Each column is a pivot column. And that means that the columns of the standard matrix, right? The column vectors are linearly independent. And if that's the case, right, if you find that the column vectors of your standard matrix are linearly independent, then you have just shown me that the transformation is 1 to 1. Okay, so T is 1 to 1. All right, so no two different inputs are going to give me the same output. Right? And this is what we showed already, right? I saw this example already before, and we showed it was 1 to 1 that other way. Well, here's just an alternate way to show that it's 1 to 1. Now be careful, right? You can only do this with linear transformations, right? Only linear transformations can be written as a matrix transformation. Okay. All right, so let's continue on with more examples that we've already seen. All right, just doing them in an alternate way. So this is one I wrote earlier. Okay, so again, it was from the Euclidean Spaces. This is a linear transformation. Again, you can show the additivity property, show the homogeneity property if you want on your own, but this is a linear transformation. So I could show it's 1 to 1 or not 1 to 1 this way that I did here, or look at the standard matrix and put the standard matrix in an echelon form. All right, so same writing. All right, it's the same example. And I'm just going to quickly write the output as a matrix times the input vector. All right, so this is going to be a 3 by 2 matrix. Down the first column, the coefficients of the first input variable, so 5, 1, 1. And then down the second column, the coefficients of x2, -3, 1, -1. And then times, that input vector. All right, but again, here's the standard matrix for this transformation. Now this is not in an echelon form right now, but I could put it into an echelon form. But I'm not going to do it by hand. I just want to save a little time. So I'm just going to go to the calculator and put this into reduced echelon form, or RREF, reduced row echelon form. I got my 84 plus here. All right. Go to the matrix menu, over to edit. Now this is a 3 by 2, but if I enter 3 by 2 and ask to put it in reduced echelon form, it's going to come back with an error, a dimension error, because for some reason when there are more rows than columns, it's not able to do it. So I'm going to make sure that I'll bump up the number of columns by 1. I'll make it a 3 by 3, but just only pay attention to the first 2 columns, right? The 3 by 2. So I've got 5, 5, 1, 1 for the first column, and then going up, -1, 1, and 3, -3, sorry. And then just leave that last column as a bunch of zeros, because that'll stay a bunch of zeros when I put this in reduced echelon form, and ignore it, right? All right, so then go back to the matrix, over to math, scroll to RREF, matrix A that I put in here. All right, and again, ignore that last column. Now, I probably should have been able to tell you that. Look at the column. There's only 2 columns. I don't know why I'm doing this. There's only 2 columns, and you see how these 2 columns are not scalar multiples of each other, so they're definitely independent. So I should have been able to tell you that ahead of time. I don't know what I was looking at, but yeah. So 1, 0, 0, 0, 1, 0. All right. So I put this into reduced echelon form again. If you recognize that, you don't have to do the echelon form. If you say, hey, there's only 2 columns, and they're not scalar multiples of one another, so the 2 columns are independent. Therefore, this is a 1 to 1 transformation. All right. But again, if you happen to if you forget that, like I just did, and you put it into echelon form or reduced echelon form, again we see each column is a pivot column. So again, all the columns the columns are independent, and then this means that T is 1 to 1. And I showed you the example again earlier. That is exactly the same conclusion that I came to earlier in the video. Right? This is indeed a 1-to-1 transformation. So you're not going to have any case where there are two different inputs going to the same output. All right. Then another example of a transformation that is linear, right, is this one we saw earlier. This is the writing I had earlier. And we saw that this one was not 1-to-1. Okay, not 1-to-1. And yeah, so but it is linear. Okay, the transformation is linear. It does satisfy the additivity and homogeneity properties. But we're going to see in a second here that the standard matrix, the columns are not independent. Right? The columns are dependent. So here it is again. Now again, this is another one of those where it's just from Euclidean space to Euclidean space. So I'm going to very quickly write this output as a matrix. This will be a 2x2 multiplied by the input vector xy. So down the first column, the coefficients of x, 1 and -1. Down the second column, the coefficients of y, -1 and 1. Now you could put this into an echelon form very easily, but this time I'll point out, notice how the columns here, I don't know why I'm starting up there, the columns are scalar multiples, right? There's only two columns that are scalar multiples. If I multiply this first column by -1, I get the second column. Two columns that are scalar multiples. Right, so that tells me that the columns are dependent, not independent. Right, and if I were to put them into reduced echelon form, which I don't need a calculator for here, reduced row echelon form, I'd just simply be adding these rows. And it would give me 1, -1, and then there'd be a row of zeros. All right, this is in the for leading one with zeros below and above it, and then there's no leading one in the second row. And you see that not all columns are pivot columns. So either way you want to show this, either way you want to say this, the columns are definitely linearly dependent. So not all columns are pivot columns, meaning the columns are linearly dependent. So T is not 1-to-1, right? It's only going to be 1-to-1 when the columns of the standard matrix are independent, not dependent. And that's exactly what we showed before, right? Showed that this was not 1-to-1 before. Okay, now we're getting into these examples. I just got two more. We're getting into these examples that weren't between Euclidean spaces, right? So here was this one earlier, okay, where I had the from P2 to R. Now this is linear. And we showed earlier it's not 1-to-1, right? Not 1-to-1. There are two different inputs that go to the same output, right? We can find that. Well, we can show this again by writing the standard matrix for this. Now, remember how the standard matrix worked when the vector spaces were not Euclidean spaces. You worked with the coordinates, right? You worked with the coordinates relative to the standard bases for these vector spaces. And then it became a transformation that was like a transformation between Euclidean spaces, right? All right, so again, this is not 1-to-1. Let's see that happening here. All right, so P2, I'll call B the standard basis for P2. All right, that was 1x and x squared. All right, this was the standard basis for P2 for the domain. And then C I'll call the standard basis for the real numbers. Now the standard basis for the real numbers is just the number 1. Right, it's just a set with the number 1 in it, right? Because every real number is a multiple of 1, some scalar multiple of 1 where the scalars are real. And it's only one-dimensional, right? This is 3-dimensional, so it should have 3 vectors in a basis, right? This is 1-dimensional, so it have 1 vector in the one number in the basis. All right. Now to get the standard matrix, look at the output here. Now again, let's say P of x, right? Let's have this P of x here. I'll write this as, what does every polynomial of degree 2 or less look like? And I'm going to write it in this order, right? Order of constant, first degree term, second degree term. So say a plus bx plus cx squared, like that. All right. Now, what I'm going to do is, right, put that in terms of the coordinates. What are the coordinates of p of x? The coordinates of my input with respect to basis b. So that would be a, b, c, right? And this is with respect to basis b here. So this means a times 1 plus b times x plus c times x squared. Change things to their coordinates with respect to the standard basis. So that's my, this is the input. Right? This is all dealt with the input, and then the output. Right, was this integral from 0 to 1 of p of x. So the integral from 0 to 1 of a, the input a plus bx plus cx squared dx, and that would be equal to, just a plus b over 2 plus c over 3. Right, again, just simple integration, plug in 1, plug in 0. So then the coordinates of this output, right, the coordinates of this output here, right, with respect to basis c, is just this number, right? Just this, a plus b over 2 plus c over 3. Okay. All right. So what we have here is I can rewrite this, right? I can rewrite this rule in terms of the coordinates with respect to these standard bases. So we have t of, and then a, b, c is the input now. But again, remember this is with respect to basis b. Right? This input became this vector is equal to, and then this, this is a 1 by 1 here, and this is a 3 by 1. This is a 1 by 1 matrix, a plus b over 2 plus c over 3. And then it looks exactly like my previous examples. Right? All the previous examples where it was between Euclidean spaces. And now I can write the standard matrix for this in exactly the same way, where I set this up. I'm going to write this output as a matrix times this input vector. So this will be a 1 by 3. Right? It's going to be a 1 by 3 matrix times my 3 by 1 input vector ABC here. Right? And that would give me this 1 by 1. Right? And again, down the first column, just the coefficients of A, 1. Second column, coefficients of B, half. Third column, coefficients of C, 1/3. And here's the standard matrix, this little 1 by 3 guy here. That's the standard matrix for this transformation. All right, but we're just looking at things in terms of the coordinates with respect to the standard bases for the domain and codomain. And it's already in that it's in reduced echelon form, in fact, because you have your for the pivot, and then there's nothing above and below it, and the lead value is a 1. So if you look at this, look at the pivots, right, that leading 1 here, and not all columns are pivot columns. Meaning the columns are dependent. The columns of the standard matrix are dependent, meaning that this particular transformation is not 1-to-1, as we saw earlier in the video. Right? All right. Okay. just like we saw earlier in the video, but just, again, another way of showing it. If you have if you have a known linear transformation, right? If you already know or have shown that your transformation is linear, then you should be able to write it as a, the output as a matrix times some input vector of coordinates, and then look at that standard matrix. All right, my final example is, again, just a repeat. Here's a repeat one. All right, we saw this one earlier. This is a linear transformation. Again, from P2 to P4 now. Just, so what I'm going to do is I'm going to use coordinates instead. Right? We're going to look at the coordinate vectors of inputs and outputs with respect to the standard bases for P2 and P4, and set this up in a way that's similar to going between R3 and R5. Right? Because remember, this is 3-dimensional and 5-dimensional vector spaces, P2 and P4. And we'll show that, T is 1-to-1 this time, right? With the again, so we have a linear transformation. Again, you can show it's linear, show that the additivity property and homogeneity properties hold. And yeah, so here again, P of x. All right, so again, I'm gonna change my input into coordinates. Oh yeah, let me write the standard bases, right? So say B is the standard basis for the domain. Right, again, that was a P2. So again, 1x squared is the standard basis for the P2. And then say C is the standard basis for P4. So 1x squared, x cubed, x to the fourth. Right? There's the standard basis for P4. All right. And then we'll see. Well, I'm going to change my inputs to coordinates. Right? So input. So again, P of x here. I'm going to write it, what does a polynomial from P2 look like? And I'm going to go in the same order I wrote the basis vectors. So again, A times 1 plus B times x plus C times x squared. So the coordinates, right, the coordinate vector for this with respect to basis B is the vector with components A, B, C. Right? It's a 3-by-1 vector. And again, this means you have A times 1 plus B times x plus C times x squared, right? You just have to remember what the basis B was. All right, and then for the output, again, I'm going to change my output to coordinate vectors as well. The output was just, x squared times P of x. And that would be ax squared plus bx cubed, multiply all these by x squared, bx cubed plus cx to the fourth. And we're changing this, right? We're writing this in terms of C. We're writing the coordinate vector of this output with respect to basis C. All right, so that would be a 5-component vector because there are 5 vectors in the basis for C. This has no constant, right? So 0 times 1. And then this has no x to the first term, so 0 times x. So my first two components are 0 and 0. And then I have a times x squared, then I have b times x cubed, then I have c times x to the fourth. So the last 3 components are a, b, c. All right. And then I could use these coordinate vectors here to change my little rule into a rule that's similar to what we saw between Euclidean spaces. All right. So T of, and then this a, b, c, right? And again, these were the coordinates with respect to basis B, the basis for P2, would be equal to, and then here's the coordinates with respect to basis C for the output, 0, 0, A, B, C, and this is with respect to basis C. We can we can change our rule the way it looked up here between P2 and P4 down here to a rule that looks like it's from R3 to R5. Right, even though it's not, right? These actually represent, polynomials. It's just they're the coordinates of the polynomials. And then, as I did before, right, with the Euclidean space linear transformations, I should be able to write this as a matrix transformation. I should be able to write this output as a matrix times the input vector ABC, and this will be a 5-by-3. 5 row 3 column. Down the first column, the coefficients of A in the output here. 0, 0, then 1, then no A and no A. Then the coefficients of B, 0, 0, 0, 1, 0. Then the coefficients of C, 0, 0, 0, 0, 1. There's your 5-by-3 multiplied by the input vector ABC. Okay, this would give me this multiplying these two matrices would give me this 5x1 matrix here. Here's the standard matrix. Then this 5x3. There's the standard matrix for this transformation. And look at it, it's already in reduced row echelon form or reduced echelon form. It's, it's got, well, okay, hold on. It's, I guess it's not really, sorry. Yeah, you got all these lead ones with zeros below and above them, but remember, all in echelon form or reduced echelon form, any rows of zeros need to be at the bottom. So if I were to truly put this into reduced echelon form, right, the matrix would look like this. I just move these two rows to the bottom, these two rows of zeros. All right, very quick and easy. And look, now it's in reduced row echelon form. Look at the pivots, these leading ones with the zeros above and below them. Each column is a pivot column. Meaning that all the columns of the standard matrix are independent, linearly independent, which is what we want when we're trying to show that indeed this transformation I started with, right, this t of p of x equals x squared times p of x from p2 to p4, t is 1 to 1 or injective. All right, and this is, again, we showed this earlier. I did show that this was 1 to 1 that other way. It's just, if you know it's a linear transformation, if you have shown that the additivity and homogeneity property hold, if you know it's linear, you can write the standard matrix for that transformation, and then, determine if the column vectors in that matrix are independent or dependent. If they're independent, the transformation is 1 to 1. If they are dependent, the transformation is not 1 to 1. Wonderful. All right, so I hope that made things a little clear there. I hope you have fun practicing problems like this on this kind of stuff, showing that transformations are 1 to 1 or not. And thank you very much for watching.